welcome back to the latest lecture session. Again, a quick recap of what we have been up to. So, in the context of soil and sediment remediation, right, we looked at different phases, right, and in this particular case of soil vapor extraction, we were looking at the wetter zone, or let us say the unsaturated zone out there, right, where we have air entrapped, right, and let us say if you have a volatile compound or a hydrophobic compound that is also volatile, let us say, you will have contamination of that particular gas, right, or the air entrapped there, or contamination of the air entrapped in that particular zone. So, in that context we looked at soil vapor extraction, yes. So, we looked at soil vapor extraction. So, in that context we discussed various aspects, as in what are the relevant aspects that you need to look into, let us say when you are trying to set up soil vapor extraction, right, as in we need obviously a source of vacuum, we need extraction wells, right, to remove or to extract the relevant gas, and also you need to have either an active or passive injection well, right. You will also need to have monitoring wells, and you will also need to have a permeable cap or impermeable cap out there, right. So, we looked at those aspects and then moved on to looking at, let us say, I believe calculate the total mass, right, or M total, right. In that context we looked at the contaminant present in the water or in the aqueous phase, in the soil, in the gas, and then in the NaPl, right, and we looked at relevant aspects. But one aspect obviously that we need to consider in this case is the partitioning between the gaseous and aqueous phase, right, as in if a compound, let us say, which is relatively volatile, let us say, or is volatile, let us say is in the aqueous phase and you expose that to air, let us say, right, what is going to happen? It is going to change phase, and there is going to be an equilibrium between the compound that has changed phase from the water into the gaseous phase, right, or the compound in the gaseous phase to the compound in the aqueous phase. And in that context we looked at something called Henry's constant that gives us an idea about the concentration in the gaseous phase, typically expressed in terms of the partial pressure times the concentration in the aqueous phase, right. This is what we have, and depending on the units of H, you can also have concentration in the gaseous phase to the concentration in the aqueous phase, such that H is dimensionless. And as we mentioned, let us say depending on the units of H, you will choose the relevant variables, or depending upon the relevant variables that you have, you will choose the relevant Henry's constant, let us say, right. So, that is something to look into or consider when we go about it, right. So, in that context we were looking at design, right. So, in the context of design, let us say what are some of the aspects to consider. So, this particular soil vapor extraction is similar to if I may say so, pump and treat, right. In pump and treat we try to estimate the plume size or the contaminated plume size and distribution, and then based on the Havendel et al. Design, more or less an analytical model, let us say, right, we put up or we decided where to place the relevant wells, right, as in let us say if this is our particular plume and this is the source of contamination, groundwater is flowing in this direction and this is the top view, right. So, let us say we decide on based on the Havendel et al. Design, we can choose different permutations, let us say, with respect to the number of wells, the spacing between the wells, right, and so on and so forth, and we could come up with it. So, similarly here we can look at analytical models, but typically it has been because of considerable variation from site to site, let us say, the ability of these models to predict the relevant behavior is relatively less, let us say, so, or has been relatively unsatisfactory. So, people typically look at, let us say, more or less cases based on the site, I guess, right. So, in this context, what do we need to typically look at the site, let us say. So, based on you putting in your vacuum source of vacuum, right, you will be able to come up with a radius of influence, right. And this radius of influence is defined in different ways, right. What is this radius of influence now? Let us say I have my particular extraction well or the vacuum source at this location. As I move further away from it, obviously the effect of this particular vacuum source is going to decrease, right. So, let us have this side view here, and let us look at that. Let us say this is my soil surface, let us say, and this is my extraction well, let us say, or let us say my vacuum source. So, let us say as I move away from it, the pressure, let us say, is going to be decreasing, right. So, I am going to have to look at a particular threshold, let us say, of the pressure. For example, is it 0.1 or so on inches of water? Typically, we measure it in terms of inches of water. So, one set of what do we say, people define it in terms of either 0.1 or 1 inch of H2O or inch of water, let us say. That is the pressure that the minimum pressure that should exist, let us say, at that location for that particular point to be considered within this particular radius of influence. As in from this side view, if this is the extraction well, what can we say, and this is the radius of influence, let us say all this is the radius of influence, we can say that all the points within this zone, let us say, experience a pressure or vacuum pressure greater than 0.1 or 1 inch of H2O. So, outside this particular zone, let us say, that level of pressure is not maintained, let us say, right. So, that is something to keep in mind, and others have mentioned something like either 10% or 1% of pressure at the well. For example, you maintain some pressure out here x, let us say, some people, let us say, based on their particular definitions, or quite a few people rather, have looked at 10% of x, right, for the threshold to define the radius of influence, right. So, different ways to define radius of influence, yes. So, once you define the radius of influence, what do you need to look at? Obviously, the placement of the wells, let us say. Typically, you look at overlapping patterns here, let us say, right, and go about it. Keep in mind that unlike groundwater, let us say, here we do not have this particular trapped air, let us say, moving in, right. So, it makes the job relatively easier, let us say, relatively, if I may say so, at least with respect to the placement of the wells. Why is that? Because for the particular case of pump and treat, when we are trying to pump out the groundwater, we had to look at the placement of well, because the radius of influence was something that had to be taken into mind, keeping in mind that the groundwater flows, right, because there is a gradient and thus the groundwater will flow, thus you had to take those into account, right. So, again then we are going to look at placement of the relevant wells, right. So, we will look at one example now in a couple of minutes, but before we go further, we will talk about, let us say, one particular aspect or a couple of aspects, as in what are some of the other enhancements that we can look at, let us say, as in, right, other than air sparging, let us say, what else can you use this in conjunction with, right. So, one aspect I think we talked about briefly was bio-venting, let us say, right. So, either if you want to increase the what do we say kinetics, let us say, or biodegradation, let us say, or biodegradable capacity, let us say, or the natural attenuation capacity of a particular system, you obviously need to introduce the relevant what do you say nutrients, electron acceptor or electron donor. So, sometimes let us say, or quite often rather, this particular soil vapor extraction is used to, let us say, introduce one of these relevant aspects, typically the electron acceptor, which is oxygen, right. So, it is used in conjunction with what do we say relevant aspects to promote biological degradation, and thus we end up with bio-venting in that particular case, let us say, right. So, the next aspect again that we are going to consider is bio-slurping, right. That is something again used in conjunction with what do we say one's objective, let us say, to also remove the NaPl at the same time, right. What do we have here? We have bio-slurping, let us say. And for example, when do we use this? Let us say this is again, let us say, the side view out here, the side view, right, and this is the groundwater level, let us say, and let us say you have some LNaPl out here, right, and you also have contaminated air out here, right. And so, let us say typically bio-slurping, you also extract the LNaPl, let us say, right, or the less dense or light non-aqueous phase liquid, along with pumping out the relevant gas out there, right. So, it can be done in conjunction, and that is something that is called bio-slurping, let us say, right. And there are other aspects too, right, typically that can be used to either enhance the effectiveness of this particular soil vapor extraction. So, what is one way to go about it? Let us say you have this particular soil or sediment that has this contaminant adsorbed onto it, and if it is very volatile or highly volatile compound, obviously once you remove the gas that is in contact with this particular soil, what is going to happen? Again, there is going to be a change in phase of the relevant contaminant from being adsorbed onto the soil to being transferred into the gaseous phase. But let us say if it is not greatly volatile and you want to cut down on the time required, let us say, to remediate, let us say, right, what is going to be the case here, right. So again, as I am saying, let us say maybe kinetics sometimes can play a role. Kinetics of what now? Kinetics of changing phase from either the aqueous to the gaseous or from the solid to the gaseous and so on. Kinetics too plays a role, as in until now we have looked at only the equilibrium case, right, as in the system has enough time or is fast enough to reach equilibrium within the relevant time frames, right. But let us say time is an issue, as in changing the phase is also a rate limiting step. Let us say, what do you need to do to enhance that? Let us say you can have you can heat the relevant system, let us say, right. Heating by different means, let us say electrodes or such, or thermal enhancements, that is what we are talking about. So we apply heat, as in you are supplying energy obviously, and that helps in, let us say, changing the phase of the contaminant from solid to the gaseous, let us say, right. Again, you can look at relevant potentials and so on, and that is where the relevant concept comes in, let us say, right. You want to be able to supply enough energy for the, what do we say, bond of attraction to be broken, if I may say so, in layman's terms, between the contaminant and the soil, let us say, right. So that is something to keep in mind. These are different aspects or enhancements that can be looked at, right. So now we will move on and look at a relevant example here, right. So let us look at what we have here. We are going to calculate, obviously, let us say for this site that is contaminated by benzene. What are we going to calculate? We are going to look at that, and this is something we typically need to use in, as an, if you do not know, or some of the variables are not given, you obviously need to look at the relevant literature and get those relevant aspects, or you need to make, what do we say, working assumptions, let us say, right. And typically they are based on, let us say, conservative estimates or such, but we will look at what they are. That is what we have out here, as in you need to make typical assumptions here, right. So what is the first aspect here? What is the estimated mass of the contaminant to be removed, right. For example, let us say now we are going to use this particular set of information, as we are going to see, to be able to try to design a particular system. Again, a simplistic design more or less, right. Obviously, to design the system you need to know what is the mass of the contaminant and in what phases is it present. So obviously we need to be able to look at that particular aspect, right. And then let us say what is the effect of gas flow on the radius of influence of wells. Rather, gas flow, I guess here they are combining both the vacuum source and the extraction wells, let us say. So what is that effect on the radius of influence of the wells? That is something we are going to look at. And also what is the number, placement and flow from the wells. Obviously, let us say depending upon the number of wells that you place and the amount of flow from those wells, you are going to have to look at the relevant placement, right. So that is something you need to look at, and thus we are going to look at the time required to remediate the contaminated site, right. Obviously that is something that is going to be used to, let us say, as we have seen in quite a few case studies, we have seen, let us say, preliminary studies, let us say, to be able to look at, let us say, is it feasible or not, let us say, or remedial investigation, let us say, or feasibility studies, right. That is something as we have seen people do typically or needs to be done. So in that context, you are going to have to calculate some of these aspects to see, let us say, if the system is feasible, or if the system of applying soil vapor extraction, pardon me, to this particular remediator or any particular contaminated site is a feasible option or not. You need to get those relevant aspects looked into, right. So let us move on. So what do we have here? So here we have results of the gas flow tests, right. And how are we measuring this vacuum? In inches of H2O. In is obviously inches of H2O, right. And what do we have? We have obviously metric of distance. This is the distance from the well, let us say, right, distance from the well, 0.1 meter, 5, so on and so forth. And we have three kinds of measurements, one for 0.02 meter cube per second, one for 0.01 meter cube per second, the other for 0.005 meter cube per second. These are the flow rates of the gas that is being pumped out, let us say, from that particular well, and we are trying to measure, let us say, how is the pressure changing as we move away from the relevant well, right. So obviously let us look at this particular set of data, as in obviously nearest to this particular well you are going to have or experience relatively higher pressures. So obviously for 45 here, 31 inches of water, 25, and why is it decreasing? Obviously because the flow rates are decreasing out here. This is the flow rate of air, let us say, right, or the gas flow here, right. So greater the gas flow that is being pumped out or gas that is being pumped out, the greater the pressure, let us say, or vacuum pressure, let us say 0.1 meter from the relevant well here, let us say, right. So now let us look at this particular set of data. So here as we go down, the distance from the well is increasing, right, 0.1 to 35, and thus what do you see now? Obviously, as you see, the influence and thus the pressure is decreasing now, right. So, same case out here from 31 to 0.5, 25 to 0.06, pardon me, right. So, these are some data that we have from the relevant field, let us say, right. We are going to use this obviously later on. Some of the physical characteristics are given, as in the Wedo zone or the unsaturated zone thickness is 5 meters, okay. Intrinsic permeability, air viscosity, total gas porosity, liquid porosity, bulk dry density, fraction of organic matter, and so on. Again, keep in mind that let us say just because you have a lot of data out there does not mean all the data is going to be useful to you, only a few of these particular aspects are going to be relevant to you, let us say, right. So, again that is something that we have out here, results of gas flow tests, physical characteristics, and lastly let us say, and considerably important, let us say we have the results of the soil gas sampling, let us say, right. And what is the gas that we are trying to look at? It is of benzene, let us say, right. So, let us look at what we have out here, right. Data shown in the following table were obtained by analysis of samples that were taken 3 meters, let us say 3 meters below the surface at points on a grid. So, there is a grid, let us say, with spacing of 10 meters, let us say the grid spacing is 10 meters. The numbers represent the concentration in grams per meter cube of benzene found at the corresponding grid point. So, one aspect, as in you have grids, let us say 1, 2, 3, 4, spacing between the center to center of the grid is what is it now, 10 meters, and keep in mind that though they have taken a sample 3 meters from the surface or below the surface, right, keep in mind that we have the data that says that Wedo zone is 5 meters thick. So, obviously for for the conservative estimate, we are going to consider that whatever concentration that we have at that particular 3 meters depth is the same throughout that 5 meter depth, right. So, that is something to keep in mind. And here let us say obviously I have the table here and I arrange that in such a way that they can seem like a grid, but obviously it does not turn out to be a square as it should be, but rather a rectangle. But for visualization purpose, what does this mean? So, as in we have a grid here, right, this is one grid, second grid 1, 2, 3, 4 let us say, and distance between these grid center lines is 10 meters, and let us say the average concentration within this particular grid is given here 3.7, 12 gram per meter cube, and I think 14 and 1.2 or 1.4 and 1.2, I am not sure, 4.1, 28 and so on, let us say, right. So, as you can see here, let us say, right, if depending upon the concentrations that we have experienced or looked at, the source seems to be somewhere out here, let us say, maybe out here, but maybe it can change to depending upon these concentrations of the relevant gases, let us say the source seems to be somewhere out here. Again, you can look at it in greater detail though, right. So, again the distance between let us say the grids is what do we say 10 meters, right. So, what is the width and the length? Obviously, it is going to be center to center, I guess 40 meters, is it? So, 10, 20, 30 and including these two what do we say pieces, we have more or less 40 meters. So, 40 by 40 I guess, right. Hopefully, let us see what we have out here. So, that is what we have here. So, the first aspect is we need to obviously estimate the mass of the contaminant, right, and that is for that particular aspect we have a particular formula we came up with. So, here we are assuming that there is no NaPl, right. So, we will assume that there is no NaPl, and with no NaPl being present, how did we calculate the total mass m equal time equal 0 or m total? How did we calculate that? So, we have the concentration of the relevant contaminant or contaminant present in the water, the soil and the gaseous phase. So, let us write them in that particular order. So, porosity of water times volume, total volume will give you the volume occupied by that particular water. It is not porosity of water, but I guess the fraction of the total porosity that is occupied by water. It is not obviously porosity of water times the concentration of the water plus total volume bulk density into Q. Q is the what do we say concentration of the contaminant adsorbed onto the soil, right, plus again the porosity occupied by this particular, what is this now? Here we are talking about the gas, volume, total volume into concentration in the gas phase, right. So, what are some of the phases or relationships that we have here that will make or allow us to make this particular equation simpler, let us say. Obviously, we have 3 phases gas, water and compound adsorbed onto the soil, let us say. and obviously there are going to be equilibrium relationships here, right. So, let us look at some of them. So, we have looked at this particular case quite often. Q, which is the concentration of the contaminant adsorbed onto the soil, is going to be in equilibrium with the concentration in the water, right. So, that is something that we looked at, and also we know that similarly let us say we are going to have an equilibrium for the compound, let us say between it being in the gaseous phase and the aqueous phase, right. So, that is given by Henry's law, let us say, which is going to be Cg by C in the water, let us say, right, or concentration in the water. Again, as I mentioned, we need to look at the different units of Henry's constant out there, right. So, let us go ahead and plug them in here. So, we are going to have V total, right, concentration. So, again here as you saw, we always had, what do we say, in our particular question, all the data that we had were in the units of concentration for gas, let us say. We did not have the concentration in the aqueous phase. So, we are going to have to transform this equation into the in terms of the concentration in the gaseous phase. So, let us do that. So, this concentration of the relevant compound in water is going to be equal to Cg by H, right. So, Cg by H plus total volume, bulk density Q is Kp times C, C is Cg by H, Kp Cg by H plus porosity occupied by the gaseous phase, volume in concentration of gas. So, I think I can take out V and Cg, right, V and Cg, and that is going to be equal to porosity here and V is out there by H plus rho B Kp by Henry's constant plus porosity here, right. So, using this particular equation I can estimate the mass of the contaminant in this particular scenario. Obviously, I need to calculate the volume out here, right. So, again Henry's constant from the relevant literature is out here, but as you see, what are the units here? This is the case when Henry's constant is equal to partial pressure of the relevant compound in the gaseous phase by the relevant concentration in the aqueous phase. Why is that? Because the units are atmospheres per moles per meter cube, let us say, right. That is what we have out here, right. Obviously, we need to transform that, right, into dimensionless, because we are looking at H equal to Cg by C. So, obviously, if you look at PV equal to nRT and so on, let us say, right, you will obviously need to divide by RT typically, that is what we have out here. So, I am trying to make it dimensionless here, and the dimensionless constant is more or less 0.196. So, what does that mean? We have 0.196 to be the concentration in the gaseous phase to the concentration in the relevant water, let us say, right. So, that is what we have out here for benzene, okay. So, let us move on. So, KOC I guess is what do we say, given, right. So, the average of the measured concentrations is required, right. So, obviously, here there are some issues, as in let us say for one grid itself we are trying to obviously approximate the relevant concentration by one particular sampling point. So, here also we need to be able to calculate the, let us say, the average over the entire area, but why is that required though? That is required because typically later on, let us say you are going to have to use, let us say, the terms for calculating the time required for remediation, or even in this particular case now, let us say when we are trying to have to contact the concentration, calculate the concentration in the gaseous phase, right. As in this equation we have concentration in the gaseous phase, but as you remember, let us say we have seen that we have different grids and we have different concentrations in the relevant gaseous phase, right. Different concentrations in the gaseous phase for different grids, let us say, right. So, obviously, there are two ways to go about it. One way, maybe not a great way, is something that I have here, as in I am going to take the average gas concentration as the average of the measured concentrations. That is obviously not a great way, or let us say maybe I can look at calculating the masses individually and so on, let us say, right. So, let us just try to look at that particular aspect. So, here let us say I have all the different grid numbers, right, and I have all these particular aspects out here, and I can calculate the relevant the average concentration in this particular manner, right. So, that is something that can be done, yes, and let me move back to that. So, I have 14.25 out there. So, that is what we have here, and volume I guess, right, as we mentioned, grid size is 40 by 40. We had I think 4 grids square, right, 1, 2, 3 and 4, and same case like that out here. Center line to center line or center point to center point, it is 10 meters. So, its entire length is 40 meters, same case the width is 40 meters, and depth as we saw or was given in the question, or of the as in the depth of the saturated zone or unsaturated zone or the vadose zone was 5 meters. So, from that we get a volume of 8,000 meter cube, right, and that is something that we have out here. So, Kp, obviously this is the partitioning coefficient which we use in Q equal to Kp times C, right. So, that depends upon the fraction of organic carbon. Again, why do we need to look at fraction of organic carbon here, which is this particular variable here? It is because let us say you are going to have what do we say, the organic compounds present or organic fraction in the soil, and this organic fraction is what actually adsorbs the relevant contaminant here, let us say, right. So, that is why you need to look at that. I guess it was given at 1.2%, and that is why we have FOC here. KOC for benzene, again this is from literature, and changing the units we have this, and so the partitioning coefficient is out here 0.996 liters per kg now, right. So, let us go ahead, again porosity in the gaseous of porosity or the total porosity, let us say 0.2 is occupied by gas, 0.02 by water, I guess, right, and bulk density is out here. Again these were given in your particular relevant question, I guess, right. So, the total mass is nothing but this is total volume, and this is concentration average in the gaseous phase, right. And let us look at the variables that we have out here. This is probably going to be equal to, let me write it down, I guess, right. This is certainly going to be Henry's constant, right, by H. So, it is going to be what by Henry's constant plus rho b Kp by Henry's constant plus in the gaseous phase porosity, right, the gaseous phase, and that is what we see out here 0.02, 0.196 and so on and so forth, right. And now let us see what it is that we end up with. We have 1.1 into 10 power 6 grams, right, or let us just calculate that, let us see. So, 1.1 into 10 power 3 kg, let us say, almost a 1 ton of the relevant compound, let us say, right. Again this is both in the what we say, not both, it is between, let us say, or it is among the soil, gas and the aqueous phases, right. So, we end up with what do we say, almost a ton of that particular compound out here, right. So, let us move on, let us see, right. So, the second aspect, part B, was to look at the effect of gas flow on the radius of influence here, right. So, again how do we go about this though, right. We are just trying to understand the system in terms of the data that we have here, right. So, if I look at the top view, let us say, or even the side view could have been done, but again top view, let us say this is my particular gas flow or extraction well, let us say, and out here we had earlier, if you look at it, that 0.1 distance we had around 45 inches of water, so on and so forth. We ended up with something like 0.05 or something like that inches of water, right, inches of H2O, right. And this was the case for what was it now, for I believe when the flow rate of the gas was 0.002 meter cube per second, right. And obviously we had the relevant data for different cases and so on, and different cases as in for different distances and also for different cases of flow rate, let us say, right. So, obviously we need different flow rates because later on you will need to have to choose between different flow rates or interpolate between them, right. So, that is something to keep in mind, but I am almost out of time. So, let me just quickly look at what we are going to do and wrap this up for this session, I guess, right. So, we are going to have to look at effect of gas flow on radius of influence, let us say. So, obviously we need to come up with one particular definition of radius of influence, as in if you remember people typically looked at either 0.1 inch or 1 inch of water let us say the pressure, right, to be able to define the radius of influence, or also looked at 10% of the initial pressure to define the radius of influence, let us say, right. So, but 10% or 1% of the initial pressure, that is subjective, as in initially let us say if I had 50 inches, then the threshold is going to be 5, I guess, right, but initially if I had only 10 inches, then it is going to be 1 inch. So, it is considerable variation between the threshold of 5 and 1. So, to have a uniform what do we say reference, let us say we are going to choose this particular case 1 inch of water for our particular radius of influence. So, let us look at how we are going to take these aspects into account and design for the system further, but I guess since I am almost out of time, I will continue this in the next session, and thank you.